Lesson 4.3, Trigonometry Extended, the circular function. So our goal in this lesson is to be able to find a trig ratio of any unknown angle and the trig ratio of any known angle using the 16-point unit circle. The trig ratios that we've set up so far have all been restricted to acute angles, in other words, first quadrant angles. But there's no reason to restrict ourselves to acute first quadrant angles. What we're going to do in this lesson is learn that trigonometry can apply to an angle in any quadrant. And it can apply to angles that are of any size. They can be any size in the positive direction and any size in the negative direction. So we're going to start with setting up ratios where we actually don't know what the angle is, because it's not the angle that we really need to know, it's the ratio of the sides that we need to know. And then we're going to look at situations where I do know the angle, but it's only going to be a certain set of special angles using that 16-point unit circle that we talked about in the last lesson. So let's start with trig of any angle of any unknown angle. So we're going to use concepts of right triangle trigonometry to set up trig ratios when I don't know the angle, which is the same thing I did at the very beginning of lesson 1. I would give you a triangle and then we would simply set up the trig ratios based on an angle, but never actually knowing what that angle was. Now, of course, we could use inverse trigonometry to figure out what the angle is using our calculator, but that's not what's important. What I want to be able to do is set up ratios. So imagine I give you a coordinate, and that coordinate could be in any quadrant. A coordinate is always made up of two values, an x value and a y value. Now that coordinate lies on the terminal side of an angle. So in this case, the angle theta would be starting at the positive x-axis and going counterclockwise to the terminal side, which in this case happens to be in the second quadrant. Now, based on our right triangle trigonometry that we learned in the first lesson, I would have no idea what to do to set up a trig ratio of this particular angle, because there's no triangle where I could define an opposite side, an adjacent side, and a hypotenuse. Or is there? Remember, trigonometry is based on right triangles, and right triangles can always be found by using the x-axis. Always remember that we measure our angles with respect to the x-axis. Now, generally, they're measured with the positive y-axis, but on occasion it can be useful to measure with respect to the negative x-axis. In this case, we're going to create what's called a reference triangle. We're going to set up our trig ratios not based on this angle, but based on this angle right here. We call that a reference angle because it's in our reference triangle. We need a right triangle to use to set up our trig ratios. Well, there's a right triangle right here, so that's what I'm going to do. Now, please don't make the mistake of creating your triangle with respect to the y-axis. It's always with respect to the x-axis. That way, our angle is always the same angle from person to person to person to person. If some of you do it with respect to the x-axis and others do it with respect to the y-axis, well, then the math just doesn't work out. So if you're in any other quadrant other than the first quadrant where the triangle is kind of implied for you, just create your third side by connecting the terminal side of your angle to the x-axis, either by, if you're in the second quadrant, dropping it down, or if you're in the third or fourth quadrant, basically drawing it up, always to the x-axis. So if I have the coordinate xy, which is somewhere along that terminal side of the angle, then that xy actually tells me two things. It tells me two sides of the triangle, because x is simply the distance along the x-axis, and y is the distance along the y-axis. Now, in this case, since we're in the second quadrant, the x value would have to be negative and the y value would have to be positive, but that's perfectly fine. We can have trig ratios that are negative. There's no reason we can't. It's only in the first quadrant that everything stays positive. So just like an angle, which is allowed to be negative now, trig ratios can be negative as well. And the combinations of positives and negatives also tell you which quadrant you're in. If the x is negative and the y is positive, I'm in the second quadrant. Vice versa, I'd be in the fourth quadrant. If both are negative, I'm in the third quadrant. So we have to pay attention to positive and negative because it also tells me location of the angle. Now, if we have x and y for the sides, we also need a name for the hypotenuse. Of course, it has a name. The name is the hypotenuse. But what we're going to start to see is that trigonometry is directly related to circles, hence the name of the section, the circular function. Instead of calling the hypotenuse, let's keep with the theme of circles and throw in some circle terminology. Let's call the hypotenuse the radius. Because imagine you have a circle where the origin would be the center and then xy would be a coordinate on that circle. Then r is the radius between the center and some point on that big circle. And of course r, by using the Pythagorean theorem, can be found simply by doing the square root of x squared plus y squared. Now, by calling the three sides of the right triangle x, y, and r, this allows me to slightly redefine my trig definitions. Instead of using the terminology opposite, adjacent, and hypotenuse, we can say x is the adjacent side, y is the opposite side, r is the hypotenuse. So my trig ratios actually become a little bit simpler in order at least to write them down. I don't have to say sine of theta is equal to opposite over hypotenuse. I can say sine of theta is equal to y over r. Cosine is x over r, tangent is y over x, cosecant is r over y, secant is r over x, cotangent is x over y. So it's still the same old trig definitions, we're just using a slightly different vocabulary. We're kind of simplifying things in my opinion. So instead of saying opposite, I say y, instead of saying adjacent, I say x, instead of saying hypotenuse, I say r. So let's use that concept to answer some questions. So let's start with basically the same way we started in section 1, by setting up all 6 trig ratios. So let's find all 6 trig functions of theta if theta is an angle in standard position whose terminal side contains the point 2, -3. So in this situation, I'm not giving you a triangle and finding all 6 trig ratios. I'm giving you a coordinate that you can use to build a triangle and then find all 6 trig ratios. So let's look at with this one together, and then I'll give you the next couple on your own. So the first thing I need to do is figure out which quadrant I'm in. Well, the coordinate 2, -3 is obviously in quadrant 4. So I can draw an angle in quadrant 4. Now I'm not going to really waste any time putting any tick marks on my x and y axes to represent a scale. I'm just going to say some arbitrary point on this angle, on the terminal side of this angle, is going to represent the coordinate 2, -3, and then draw my triangle, remember, always with respect to the x-axis. So I'm not going to draw my triangle this way, I'm going to draw my triangle this way. So that creates my reference angle, and since the x value is 2, I know this side would have to be 2, the y value is -3, so this side would have to be -3. Remember that x always represents my adjacent side, y always represents the opposite side. Now, of course, the only thing I have to find is the radius simply by doing the Pythagorean theorem. This is not one of my special triangles, so it's just going to be 2 squared plus -3 squared, so 4 plus 9, which is 13, so my radius would be square root of 13. Now, just like section 1, let's set up our trig ratios, starting with sine, cosine, and tangent. Now, keep in mind, the opposite side, the y value, is negative. Don't ignore the negative. The negative is just as important as the 3 is. So when I set up my sine ratio, normally I would say sine is opposite over hypotenuse, but using my new definition, I can simply say sine is y over r. The y value is -3, the r value is root 13, so -3 over root 13. We can leave it like this if it's a free response answer. If it's multiple choice, I'm probably going to have to rationalize it, so -3 root 13 over 13. Cosine is x over r, x is 2, r is root 13, so 2 over root 13 or 2 root 13 over 13. Tangent is y over x, opposite over adjacent, so -3 over 2. To get cosecant, secant, and cotangent, let's just take these 3 and flip them upside down. So remember, I'm not going to waste time with these rationalized versions. I'm going to take the unrationalized versions and flip them upside down. So when I flip them upside down, I'll get -root 13 over 3, root 13 over 2, and -2/3. All right, here are 2 more. Why don't you give these a try, hit play when you're ready. All right, so let's look at -5, -12. And the beauty of this coordinate system, now I'm probably guessing that you do a triangle just like I did on part A, but I'm actually not even going to waste my time with that triangle. Since I know my definitions very clearly, sine is y over r, cosine is x over r, tangent is y over x, and so on, I'm just following a formula. As long as I know what x, y, and r are, then it's simply plug and chug. I know x is -5, y is -12. I can figure out r by doing the Pythagorean theorem or simply recognizing that this is a 5, 12, 13 triangle. As long as I have x, y, and r, it's simply a matter of writing down your ratios. Sine is y over r, cosine is x over r, tangent is y over x. Cosecant, secant, and cotangent are just flip, flip, flip. So if you want to draw a triangle, you're perfectly fine to draw a triangle. I'm not going to stop you from drawing a triangle, but keep in mind, you don't really have to draw a triangle, you just have to know the rules. So keeping that in mind, let's look at this one now. This is a situation where even if I wanted to draw a triangle, I couldn't draw a triangle. 1, 0 is already on the x-axis. There's no height, there's no opposite side to draw. So based on right triangle trigonometry, this question makes no sense. That's the beauty of the circular function. By thinking of trig in terms of a unit circle or within a coordinate plane, we can kind of ignore the restrictions that we had with right triangle trigonometry, and we are now able to answer questions that we could not answer back in geometry. As long as we know that x is 1, y is 0, and r is the square root of 1 squared plus 0 squared, or 1, then I can set up my trig ratios just like I did before. So sine is y over r, 0 over 1, which is 0. Cosine is x over r, so 1 over 1, which is 1. And tangent is y over x, so that would just be 0. To get cosecant, secant, and cotangent, I could flip, 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 but this is probably one of the points where you may or may not get a little bit confused. How do you flip 0? Well, remember, all of these are 0 over 1, 1 over 1, 0 over 1. So when I flip them, 0 over 1 becomes 1 over 0. But of course, you can't have 0 on the bottom, so it's undefined. Cosecant on this problem is undefined. Yes, you can have trig ratios that are undefined. That's perfectly fine. It is what it is. So cosine is 1, so secant would also be 1. Tangent is 0. Flip it upside down. Cotangent would be undefined. So let's take a second look at our understanding of when a trig function is positive and when a trig function is negative. By knowing when trig functions are positive and negative, not only can it save us time down the road, because I don't have to worry about remembering to put positive 3 or negative 2, because I'll know based on what quadrant I'm in whether the answer is going to be positive or negative. It will also allow me to narrow down. If I happen to know that a sine ratio is positive and a cosine ratio is negative, then I would automatically know that I am in the second quadrant as opposed to the first, third, or fourth quadrant. Now, the way I know that is simply by knowing how quadrants work. This is the y-axis. This is the x-axis. Positive y goes up, negative y goes down. Positive x goes right, negative x goes left. Now remember, the r value is found by using the Pythagorean theorem. R is defined to be the square root of x squared plus y squared. No matter what x and y are, r is always going to be a positive number. So we can kind of ignore the sign for r. The sign only applies, the SIGN sign only applies to x and y. So, first question, where are sine and cosecant positive? Well, sine and cosecant are defined purely in terms of y and r. R is always positive, so the only way for sine and cosecant to be positive is if y is also positive, because if y is negative, a negative over a positive would be negative. So if y is positive, then sine is positive. If y is positive, then cosecant is positive. So where is y positive? Y is positive anywhere above the x-axis. So anywhere up in quadrants 1 or 2 would be a positive value for y, and thus a positive value for sine or cosecant. If I'm in the third or the fourth quadrant, y would be negative, so sine and cosecant would be negative. So sine and cosecant are only positive in quadrants 1 and 2. Let's do the same thing for cosine and secant. Cosine and secant are defined in terms of x and r. X is positive anywhere to the right of the y-axis. So in other words, quadrants 1 and 4. So as long as I'm in quadrants 1 or 4, cosine is positive. If I'm in quadrants 2 or 3, cosine and secant are negative. And lastly, tangent, cotangent. So tangent and cotangent are defined in both terms of y and x. R doesn't play a role for tangent and cotangent. So in order for y over x or x over y to be positive, well, if both of the values are positive, like in the first quadrant where both x and y are positive, then y over x or x over y is positive. But of course, a positive over a positive is not the only way to get a positive answer. A negative over a negative will also give you a positive answer, and a double negative occurs only in the third quadrant. So tangent and cotangent are positive in quadrants 1 and 3, whereas they're negative in quadrants 2 and 4 because you'd have a mix and match of positives and negatives. So, in the first quadrant, we've seen that all 6 trig functions are positive. Everyone's positive in the first quadrant because x and y are both positive. That's why when we were doing right triangle trigonometry with acute angles meaning first quadrant, everything turned out positive. We never had any negatives because everyone's positive in the first quadrant. In the second quadrant, only sine and cosecant were positive. In the third quadrant, only tangent and cotangent were positive. Everyone else is negative. In the fourth quadrant, cosine and secant were positive. So everyone gets the first quadrant, and then everyone gets their own quadrant to themselves. Sine in the second quadrant, tangent in the third quadrant, cosine in the fourth quadrant. Now, there's a quick, easy way to keep this straight. First quadrant was everyone, so we say all. Second quadrant was sine, so we say S for sine. Of course, if sine is positive, cosecant kind of comes with it. Tangent for the third quadrant, cosine for the fourth quadrant. ASTC. All students take calculus. So as long as you remember ASTC, all students take calculus, then you can remember which trig functions are positive in which quadrant. Or of course, you could always go back to the definitions. Y is positive up here, y is negative down here. So sine is positive, sine is negative. Cosine is positive, cosine is negative. Because x is positive, x is negative. Tangent is only positive where the signs are the same for both x and y, so tangent would have to be positive in 1 and 3. Or all students take calculus. ASTC. So let's look at an example where that would be relevant. Let's evaluate just the specified ratios, cosine, tangent, and cosecant, where the sine ratio is 3/5, but the cosine is negative. Notice I'm not telling you what cosine is, I'm simply telling you that cosine is negative. So immediately, if I wanted to, I could put a negative on the answer for cosine. So let's look at this one together, and of course, I'll give you the next few on your own. So, just like we did in section 1, I can build a triangle whose sine is 3/5. The question is, which quadrant should I build that triangle in? Well, we can use these two pieces of information to help us determine which quadrant we're in. Now, right here it says sine is 3/5, but what it kind of really says is that sine is positive 3/5. In other words, sine is positive. So where is sine positive? Sine is positive in quadrants 1 and 2. Well, this statement says cosine has to be negative. Well, where is cosine negative? Cosine is positive in quadrants 1 and 4, therefore it's negative in quadrants 2 and 3. So we've got two statements. Where do they agree? Obviously, they agree in quadrant 2. So since sine is positive and cosine is negative, I must be in quadrant 2. Now that I know I'm in quadrant 2, I can go ahead and build my triangle. Sine is y over r, so the y side, the opposite side is 3. The r value, or the hypotenuse, is 5. So we can just find our third side using the Pythagorean theorem, or simply remembering, hey, 3, 4, 5, this is a 3, 4, 5 right triangle, so I can put a 4 down here. But of course, if I do, I'd be wrong, because this is not 4. This is in the second quadrant. The x value is negative, so negative 4. Make sure you are paying close attention to the sign. If you don't pay attention to the sign, you're going to get the wrong answer. So the x value is negative 4. Now I can go ahead and set up my ratios. Cosine is x over r, so negative 4 over 5. Notice it's negative, which is exactly what the given information said. Tangent is y over x, so 3 over negative 4, or negative 3/4. I'm in the second quadrant. My tangent ratio better be negative. And of course, cosecant, I don't need a triangle. Let's just take 3/5, flip it upside down, call it a day. So once you're done, double check your positives and negatives one more time. I'm in the second quadrant. Cosine is negative, tangent is negative, cosecant is positive. The signs make sense. Let's move on to the next one. So here's another one. Why don't you try this one on your own? Hit play when you're ready. So we've got tangent is negative 5/12. Sine is also negative. So I have a situation where both tangent is negative and sine is negative. So first thing I need to do is figure out which quadrant are both of these statements true. Tangent is negative in quadrants 2 and 4. Sine is negative in quadrants 3 and 4. So we've got agreement that we're in quadrant 4. We can build our triangle using the 5 over 12. But it's negative 5 over 12. So is it negative 5 over positive 12, or is it positive 5 over negative 12? Well, since I know I'm in the fourth quadrant, that answers my question. 5 is the y value, 12 is the x value. In the fourth quadrant, it's the y value that's negative. So it's the 5 that's negative, not the 12. So using my Pythagorean theorem, find the r, or of course 5, 12, 13, that's one of my Pythagorean triples, and set up my ratios. Sine would be negative 5 over 13, secant would be 13 over 12, cotangent would be 12 over negative 5.